Good morning and welcome to the next session of our Digital V-Days. I'm very happy to welcome all of you. My name is Markus Eberle and I will moderate this webinar together with Robert Schillinger today.
Good morning.
Good morning. So the topic of today is EMC debugging on flyback converters. The presentation will be about 30 minutes long, and then after that we have scheduled some time, 10 to 15 minutes, for your question. So this means you cannot ask us your questions with your microphone during the webinar, but you can ask them with the Q&A function at all the time during the webinar, and we will later on go through them. If we can't answer them now in the live webinar, we will later send you an email, so you will get your answers. And also you have the possibility always to send us an email at digital-v-days@we-online.com. So also in the next days, you will also get the link to the presentation as well as to the recording from us. So you will also get all materials for your stuff. Yeah. So that's enough from my side for the beginning. I hope you stay tuned and I wish you a good webinar and good information. And yeah, Robert, have fun.
Thank you very much, Markus.
You're welcome.
Yeah, welcome also from my side. I will start immediately because we have a lot of slides today in 30 minutes. For this, the agenda is only in the PDF for you later on. I will start with the test setup and equipment we are using for this presentation. We have here on the left side a so-called V-Listen. We are using to measure the noise which comes out from the device under test. You can see here that's the Flyback design. And on the other side, to get a lot of noise, we need a load, in this case Elektronik load, where we give the load to the Flyback. To measure the signals in frequency domain, we use this oscilloscope with a fast Fourier transformation to visualize. And the special thing in this presentation is we will split the common mode and differential mode noise into the two parts to see what happens with what kind of filter we are implementing in the design. Normally in the laboratory you are measuring the complete noise together, and you can't select what kind of noise is the reason of reaching the limit lines. Okay, some words to the Flyback itself. We use Flyback from 24 volts down to 5 volts at 5 amps. 25 watts we are using in powering. We use a controller from analog device with a switching frequency of 300 kilohertz and reach with this constellation and also with the filter an efficiency of around 90%. As transformer, you can see here, we use a PoE transformer with this article number here. And for the MOSFET here in front of the picture, we use an old TO220 device because it's easy to do much more things with this kind of case instead of a SMT part. We will start with time domain measurements with these 3 probes you can see in blue, green and red. We have here the blue one. We can measure the switch node voltage and the ringing on this node. With the red one we can measure indirectly the current, or the ripple current of the capacitor here, and with the green one we measure the ripple voltage at the input capacitor. Here we can select the snapper device. We can add or we can remove it. And in the first step we do this on these points, on these test points inside the board, and have a look at the blue one. We get the dark blue measurement. You can see here yeah, a big voltage peak around 130 volts without the snubbering, and you can also see a ringing around of 10 megahertz, which is going down. Is damped ringing, but with 10 megahertz. This 10 megahertz we will see later on in the frequency domain also. The reason of this ringing is the leakage inductance of the transformer, and together with the input capacitance of the MOSFET. And that's two parameters you should have a closer look on it if you design a Flyback converter. If we activate the snubber, we get the second blue line, and we see we drop down the peak a little bit and reduce the ringing, because the snubber design is filtering the swinging energy, and for this it drops down. So we can see at the current side, at the current transformer, we're measuring indirectly the current, but also here you can see the 10 megahertz ringing frequency. And the same like before, if we activate the RCD snubber, then the ringing drops down. Also on the input capacitor, we have a big ringing, a high voltage ringing, and also we can find here the 10 megahertz again. And also here, if we activate the RCD snubber, then it drops also down. The next point is or the configuration for the first frequency domain measurement. We add here a shortcut. We remove the common mode choke. We will use later on, and this jumper gives us activating this capacitor. It's a capacitor down to the base, to the functional earth. Then we get a feedback or a return path to the ground for common mode currents. Then we will measure in the lab-like both noise or both kind of noise together, and we get this result. We see here the first base frequency, the 300 kilohertz. We see harmonics, and we have here at the 10 megahertz a huge peak in the measurement. Here around 50 dB more than the class B limit line. We have to reduce it below this line. That's the mission for this day. Here we get around 80 dB microvolt at 300 kilohertz, and at 900 kilohertz 68 dB microvolt. It's even too much. We are far away from the limit line, and the goal is to reduce by filtering and other methods to bring this measurement line below the limit line. Some for background. The green dotted line is in principle the content of the listen we are using. It's a so-called V-listen. The yellow is a Flyback converter with some parasitics we are using. And the red and blue arrows here are corresponding for differential mode and common mode currents. We see this here inside the schematic and see what is the way the current is flowing. The same with the blue, the common mode current. You can see also here, and in this case We get some parasitic capacitances here, and this is a path down to earth where the common mode current can flow. Based on this, we get some formulas which we are using inside the oscilloscope for calculating and splitting the noise into differential and common mode. And the same we can do by a so-called splitter device we can put on the V-listen, in front of the V-listen. And then we get the same result by hardware, or you can do it by software inside an oscilloscope. Yeah. The splitted noise we see here. In the first point we see the common mode, and it's similar to the complete noise we see before. Also here around 50 dB at 10 megahertz, not microhertz, megahertz. And we have here a little less noise, 76 dB micro at 300 kilohertz. That's the reason, because we have also to the common mode also the differential mode noise, and get a little higher level if we measure both together. Yeah, the differential mode looks like so. We have here also the 300 kilohertz, here the peak at 10 megahertz. And now we activate the RC snubber. The RC snubber is in principle a differential mode solution to reduce differential mode noise, but we will see if this is the complete truth. Yeah, at common mode we have at test 2 this value, and in red we get now test 3 with activated RCD snubber. And for this we can see here in the 10 megahertz area we reduce a little bit the level with the RCD snubber, or common mode. Why we can reduce also in common mode, that's the point. We have a lot of parasitic elements which are the way for the common mode current. And the RCD snubber reduces the ringing, and if you are reducing the ringing, then you are also reducing kind of mode conversion from the differential mode to the common mode. And for this, the common mode will also affected by RCD snubber. Around 8 dB in common mode we can reduce. For differential mode we do the same and see it's also some reduction we can see. It's around 6 dB, not so much at the moment. It's one point we can do. Yeah, that's the picture from the start again. Now we do the next test, the test 4. In this test we will activate the bypass caps, the primary secondary caps here and here. That's the caps which are in parallel to the transformer to make it possible to bring the RF current from primary side to secondary side back to the primary side, and reduce in this way also common mode noise. That's the points on the boards, the jumper on the boards. One is here, the other is here. That's here and here the components itself. Yeah, now what happens? We do test 2 and 3, now test 4, and see, now we get a better result in the higher frequency, which is caused for the common mode. And if we separate 2 common mode, we can see much more. We see this orange curve and have here a kind of knee frequency or corner frequency at around 4 megahertz. That's the point here. And also here we have a little reduction of the noise, but up to now not so much. Yeah, where this 4 megahertz corner frequency comes from, we activate the capacitor C1 and C29, which are in principle in parallel. We have the capacitor which routes our common mode current down to the protected earth. And this one is in series, and if we calculate the resulting capacitance and we measure the power line of the flyback, we get also around 1.6 microhenry from the power line, and we get around 0.9 nanofarads, yes, of parasitic capacitance. And if we put these values into the swinging formula, we get here around the 4.2 megahertz. We can see also in the measurement. Yeah, that's the reason behind. Then the next step for debugging is to insert the common mode choke. We see we have a lot of common mode noise in a flyback design. For this we try on the input side this common mode choke together with the so-called Y caps here and here. And both together are against the common mode. This is a board configuration. We change the shortcuts by the common mode choke and put this jumper on to activate this in this device. Yeah, what happens? We will see in test 5 in blue. We drop down again in the higher frequency area of the conducted measurement. Get here again a corner frequency at around 2.5 megahertz, which I will explain a little bit later. Yeah, and the common mode itself, without any other noise, it drops completely down below the limit line, the blue limit line here. Everything seems fine, but from the slide before we see the sum of both common mode and differential mode is not fine anymore. And as I show you here, we can see the differential mode itself, it's not completely clean. Yeah, I say this corner frequency here, now it's a question, where does this cutoff frequency comes from? That's the first question. And how we can attenuate this differential mode noise. We have this at around 2.5 megahertz. Then we go back to some backgrounds. We measure the common mode choke. A common mode choke is also not an ideal component. We have not only the common mode attenuation of this device, we have also a so-called stray inductance of the device, and you can measure it by this configuration. You put both ends together and measure on the other side with could be a easy measurement tool to get around, in this case, 10 microhenry. Or the second possibility is to use our tool, online tool Red Expert, and show the differential mode diagram. Put a slide or a cursor to the 10 megahertz and read the value here, and you get around 633 ohms at 10 megahertz. And with this simple formula here, you can calculate from the diagram also the 10 microhenry leakage inductance of this device. This is possible for all our devices, and this and the capacitance of the power TVS diode at the input of the schematic or of the device. We can also calculate again with the swimming formula this 2.5 megahertz. The second corner frequency I show you in the measurements, And this both are caused by the capacitance of the TVS diode together with the stray inductance of the common mode choke. And now, if you have a good idea, this is a LC filter. If we support the parasitic capacitance of the power TVS diode by an additional capacitor, which is a little bit more in capacitance, then we can shift this corner frequency down or below the 300 kilohertz. What is the base frequency of the Flyback converter? And for this, we can also reduce the differential mode noise. And this is what I would like to show you here. We close this jumper here, and we have a 4.7 microfarad ceramic capacitor. We activate this one, and together with the stray inductance of this device, we get the LC filter we need for the differential mode noise. Yeah, that's the point here. This is a jumper and the component itself. And if you know a 4.7 microfarad ceramic capacitor has also DC, the so-called DC bias effects. We're working with 24 volts, and we use I think a 50 volt device. We get a drop in the capacitance, and this will also result in the corner frequency of the LC filter at the end. But I will show you a little bit later. Now we do the last test, the test 7, in a total conducted emission measurement, and see everything is fine. We are below the limit line, everything is good. Now we will have a closer look on the single common mode and differential mode parts. For common mode, we get this result. We can also reduce it again a little bit because of mode conversion effects. We can also see this in common mode. On the differential mode side, we get also such a reduction because in sum we have the goal reached. And some small words to the DC bias. You can find this also in our Red Expert tool. You get the 4.7 micro 50 volt ceramic capacitor, put the slide to 24 volts and get as end result around 3.7 microfarads at 24 volts. And then you can calculate exactly the corner frequency of the LC filter you have here. And in this example, it's completely enough to have 3.7 microfarads. That's enough. Sometimes you must have a look on it, because if the drop is too high, then the corner frequency is on the wrong place and you get not the results you like. That's also some formulas you get in the PDF. Can have a look on it, and if you have any questions in this direction, then you come back to us and ask this. Thanks a lot.
So, Robert, thank you also from my side for your presentation. And as you see right now we are here for your questions. So just use the Q&A function of the WebEx control panel and maybe have a look and send it to all panelists. So then we have a good look at all your questions. So Robert, let's start in right now. First question, which I can see here. What are sources of CM and DM noise in Flyback?
Okay. The classical, I start with the differential mode. The differential mode, the typical source is the switching frequency, the PWM inside the converter device itself. It's a switching frequency, which you can see as a differential mode noise. And all the common mode comes, especially in the Flyback design, from parasitics of the transformer. The transformer is interwinding capacitance. And this is the way for the RF current to flow from one side to the other. And if you do nothing against this, then it comes to the common mode noise.
Okay, thank you very much. Then also from the same attendee here, the following question. By looking to the graph, how can we differentiate CM and DM noise? Is there a possibility?
In principle, I show you at the start always both noises together. That's a classical measurement, I think, in the laboratory, in the EMC laboratory. If you use a standard listen, then you can see only the whole noise. If you like to split it, then you need so-called V-listen, or you need two listens, one for the plus line, one for the minus line. And in principle, with the combiner device, the hardware part, I spoke about it, or with an oscilloscope and the mathematics of the oscilloscope, you can split it by mathematics. The formula are inside the presentation. You can split it in these two parts. It's in principle an easy way.
Okay, Robert, thank you very much for the answer. Then let's go on with the next question. How can the snubber circuit improve common mode? Is this a different circuit?
Yeah, as I explained, in principle, the snubber device reduces the ringing, and the ringing is a typical differential mode noise. But why we can also reduce the common mode? That comes from mode conversion. In principle, the differential mode is the first source and converts via parasitic capacitances to a common mode. And that's the reason, if I reduce it, then I reduce also a little bit the common mode.
Okay. Thank you. Then we have still some time left and we see there are a lot of questions coming in. Let's go on with the next one. What is the difference between using the splitter board and the oscilloscope to measure CM and DM?
In principle, if you have the splitter board, you need an additional hardware part. You have also some attenuation on the board, which is sometimes not known. That's a little bit tricky. With a good oscilloscope and you use the math, you are a little bit more accurate. But in principle, both methods are very, very close to real results. We check this, and it's very, very nice results you get.
Okay, nice to hear. Okay, so next question. Is it worthwhile investigating the noise sources by measuring wiring inductance and parasitic capacitance?
Yeah, I think so, or I would say it's important, because I think the results are speaking for that, to do it, because you get a lot of information around your system, and get really, really nice information to do something against.
Okay. Then let's go on. Next question. Why is there a mode conversion, or why mode conversion happens in conducted emissions?
That's, I think, I answer also in some other questions. That's the parasitic elements inside the MOSFET, the transformer. The device itself is coupling to a base, to Earth, and this all parasitic capacitors goes to such conversions.
Okay. The next question. That's also a question maybe from my side. Are you going to share the slides of the presentation? yeah, you will get all the informations from us in the next few days. So we will send a link an email to you with the link to the recording as well as to the slides and the presentation. And also just a hint, if we can't answer all your questions now in the live webinar, we will answer them later on via email, so you will get your answers. So then let's go on. Is it better to have the secondary side connected to PE with capacitor than primary? And if so, why?
Okay, in our case, we do this explicitly because we show you a lot of things, and it's better to have specific capacitance between the secondary side and the earth. That's correct. In the other cases, it depends on the application. If you have a medical application, you have completely other solutions, like in an industrial application. And this depends, in principle, of the application. If you are able to do this or not. In principle, you have every times parasitic elements, also without concrete or a discrete component to PE. For this, I can't not really answer in the right way to say, yeah, do this or this. It depends.
Okay, thank you, Robert. Then next question, a little bit longer. Can you reduce EMI by adding components to the secondary part of the flyback and also CM choke or caps or other things? Or do you mainly need to reduce the EMI in the primary part? Take your time.
Complex question. Okay. Yeah, in our case, I think we do more on the primary side. Mm-hmm. Because in principle you have the controller also on the primary side, and this controller produces the differential mode noise, and this is on the primary side. And for this I do more on the primary side than on the secondary side. It's also it's topology dependent. If you have a boost converter, for example, you do more things on the secondary side because this is a topology which is more hot on the secondary side. But for the flyback, you do the most things on the primary side.
Okay, thank you very much. Then last question for now, Robert. How can you calculate snubber components? Is it the 1/2, or help me with this?
It's the calculation for the RC.
For switching frequency or specific harmonics.
Yeah, okay. In principle, the snubber itself should reduce the high voltage spike. That's the reason why I use an RC or an RCD snubber to reduce this, because I must protect the MOSFET. The MOSFET had a special voltage we can handle, and with the inductance of the transformer and the used MOSFET and the capacitor, you get the high peak. And this is the most point why I use it. The other effect to reduce the swinging is a nice thing. It goes into the calculation also to reduce the correct frequency. But if I remember me right, we have some more information, and I think it's the best way to give the attendee such information via email after this.
Okay, perfect. Robert, then thank you very much. Now we are at the end of the Q&A session and of the webinar itself. Thank you for your attention. I hope you enjoyed the webinar. And yeah, if you didn't get your answers already, then you will get them later on via email. So stay tuned on our digital V-Days. We still have some webinars left, and I hope you enjoyed it. Thank you very much again, Robert.
Thank you too.
And have a nice day. Bye.
Thank you. Bye.